first of all, the resubmission policy is that you first submit by, I think, October 4th, which is the deadline. And then after the deadline, you will get some feedback from the TAs or from me, and then you get to resubmit. We usually give you another 10 days to resubmit after you get the feedback. And the other point that a lot of you asked, which was very strange, was what if I don't show any effort in one of the 5 problems? Well, you will not be able to resubmit that one problem. Okay, so you have to show effort in every problem. Okay, this being said, today we're going to cover one of my favorite topics, which is graph theory. And basically the moral of today is that we don't care about geometry. So in basic geometry, for example, you've done a lot of work with triangles. And for you, this triangle would be very different to, let's say, this triangle. Okay. But today we're going to focus on problems where the geometry of the problem does not matter at all. All we care about is whether there is a connection between a pair of points. So imagine that every vertex or every point here is a computer on a network. So it's a computer on the internet, let's say. And let's say you want to send a message from one of these computers to another one. What you really care is whether there is a sequence of connections that connects your computer to the recipient computer. You don't care about the actual geometry at the lengths of the cables that are used or exactly what technology is used to connect two computers or so on. If there is a connection, you can send a message. So you can send a message, for example, from this vertex to this vertex. But if there is no connection, you cannot send a message. So these are the types of problems that we care about. And these objects, which are basically vertices, so the points are called vertices, and edges, the segments are called edges. These objects are called graphs. So my definition of a graph is this. I say a graph is a tuple, so I show my graph with G, and it has 2 parts. It has V and E. Okay, so V is my vertex set. So V is a set of vertices. Now, in most cases in this course, V is finite. So again, vertices are these points. So we're usually talking about finite graphs. We usually have a finite number of vertices. But there will be some special cases where we talk about infinite graphs as well. Okay. And then E is a finite set of edges. Okay. But what does it mean? What does an edge mean? So I would say that every edge E in E is basically a set of 2 vertices. Okay. So is of the form UV, where both U and V are in my vertex set. So for example, let's say that I give some numbers to my vertices. So let's say this is vertex 1, 2, 3, and this is also vertex 1, 2, 3. So I'm thinking of 2 different graphs. Now, the graph on the left will have the vertex set 1, 2, 3. Okay. What are my edges? Well, I don't want to use too many curly braces. So I write it like this. I just write 1, 2. But what I mean is actually the set containing both 1 and 2. Okay. So I have an edge from vertex 1 to vertex 2. I have an edge from 1 to 3, and I have an edge from 2 to 3. Okay. Now, what happens if I want to describe this graph on the right? Well, my set of vertices is again 1, 2, and 3. And my set of edges are 1, 2, 1, 3, 2, 3. So as you see, these 2 graphs are equal, because I said that my graph is just a pair of a set of vertices and a set of edges. So if I have 2 graphs that have the same set of vertices and the same set of edges, for me, these 2 graphs are the same. which is exactly this idea that I don't care about the geometry of the problem. I don't care how you're drawing it. All I care about is that I have three objects, three vertices, 1, 2, 3, and I can go from 1 to 2, from 1 to 3, and from 2 to 3. Okay? So whenever we're talking about graphs, we have problems like this. Okay, great. We just need a bunch of words in order to be able to talk about graphs, and very soon we will start solving some problems. Okay, so the first word I have to tell you about is a loop. So a loop is an edge from a vertex to itself. Okay, so an edge from a vertex to itself. Okay. Technically, this is allowed in our definition. Because if you look at my definition, I was very careful. I didn't say that the edge is a subset of size 2. I said it's a subset of this form, U and V, and maybe U and V are the same. So when they're the same, we call that a loop. So I can have something like this. This would be a loop. It would be the loop 1, 1. Okay. Now, we're usually talking about what we call simple graphs in this course. So when I say a graph is simple, I mean that it doesn't have any loops. Okay. Now, in a lot of cases, I will just say, suppose we have a graph G, it will have this property and that property. I don't say that it's simple, but I mean that it is simple, okay? Because loops are usually stupid things. Like in practice, again, just think of this idea that this is a computer network. And so imagine that each of these vertices is a computer. Then each of the edges is some sort of a network connection. It's a cable or a wireless connection that is connecting two computers. Why would you connect your computer to itself? Okay, so technically you can do this, but usually we don't care. And also there's this concept of multigraphs. And in multigraphs, the idea is that you can have several edges between the same set of vertices. So maybe I have 2 1, 2 edges. So 2 edges that go from 1 to 2. Okay. Again, when I say a graph is simple, I mean that I don't have multiple edges. And generally in this course, I'm assuming that my graphs are simple. So no loops unless specifically said that we have loops. Okay. Now, we have this concept of neighbors. Again, this is very intuitive. The idea is that if I have 2 vertices and they're connected by an edge to each other, then I say that they're neighbors. So if UV is an edge of my graph, we say that U and V are neighbors. Okay. Another word for this is adjacent. We say that they're adjacent. So in this graph, in the graph on the right, every vertex is neighbors with every other vertex. Okay. Such a graph is called a complete graph. So if every vertex is a neighbor of every other vertex, we say it's a complete graph. The opposite of a complete graph would be an empty graph. If I have no edges at all, if I just have a bunch of vertices, nothing is really connected to anything else, that's called an empty graph. Okay. And I can also define the complement. Okay. So let's say I have a graph G with vertex set V and edge set E. The complement of G is just a graph on the same set of vertices where the idea is that an edge is in the complement if and only if it's not in the original. Okay, where every possible edge UV is in the complement graph if and only if. By the way, when I write this, it means if and only if. It's basically the same as this. UV is not only. Okay, let's do a simple example of this. Let's say I have a graph with 4 vertices, 1, 2, 3, and 4. And let's say that I have these edges. Okay. And now I want to find the complement. The complement of this graph will be a graph on exactly the same set of vertices. So 1, 2, 3, and 4. But for every possible edge, I look at the original graph and I put the edge only if it's not there. So 1, 2 is already in the original graph, so I'm not going to put it. 1, 3 is already in the original graph, I'm not going to put it. 1, 4 is already there, I'm not going to put it. 2, 3 does not exist in that graph, so I'm going to put it here. 2, 4 exists there, so I'm not going to put it here. Now, 3, 4 does not exist in the original graph, so I'm going to. So if this is my graph G, this is going to be my G complements, or G bar. Okay. And just to give you some notation, the complete graph on n vertices is shown by Kn. So this is basically a graph where I have n vertices and every pair of vertices have an edge between them. Every pair of vertices are adjacent neighbors. Okay. So here's the first question. Let's say that I have this complete graph on n vertices. How many edges does it have? How many edges does Kn have? Yes, n choose 2. Because I have n vertices and I have all the possible edges. But every possible edge is represented by its 2 endpoints, but by the 2 vertices that it's connecting to each other, right? So I have to choose 2 vertices for every edge, so it's n choose 2. Now, generally speaking, it's easy to see the different complete graphs. So K0 is just a graph that has no vertices and no edges, so it's the empty graph. Its vertex set is empty and its edge set is empty. K1 is the graph that has 1 vertex, but no edges. So it's also empty. K2 is just 1 edge, right? K3 is often called a triangle because it looks like a triangle. And this was the first example that I showed you. Okay. So K4 will consist of 4 vertices, and every 2 of them are connected to each other. So this is connected to everything. This is connected to everything. These 2 are connected. Okay. And so on. And K5, K6, I'm not going to draw. So some of these graphs, again, have names. You will get used to the names. So I will always talk about a triangle in this course, and that just means a K3. Okay. And the interesting point is that, again, we don't care about geometry. So we have just 1 triangle. It's the triangle. Okay. All triangles are the same. Okay. Now, based on these things, we can also define other notions. So I can talk about a subgraph. So what does it mean if I have a graph and I say that another graph is a subgraph? So we say a graph H, let's say with the vertex set VH and the edge set EH, is a subgraph of a graph G with vertex set VG and edge set EG. Well, this is going to be very easy if the set of vertices is a subset and the set of edges is a subset. So if VH is a subset of VG and EH is a subset of VG. So basically, whenever I'm talking about a subgraph, all I mean is that I take the original graph and I just throw out some vertices and edges, and that's a subgraph. Now, we can also have this concept of isomorphism. So here's the thing. Up until this point, we were actually talking about labeled graphs. What do I mean by that? I mean that my vertices had names. I said that I have a set of vertices, and basically, so I have like vertex number 1, vertex number 2, vertex number 3 here. Sometimes I write my graphs without actually writing the names of the vertices. In these cases, I'm just assuming that you will add names to the vertices yourself, right? So K3 is actually this graph, right? But now, here's the thing. Suppose that I have two graphs that look similar. So let's say I have this graph, for example, and this one. And let's say that only the labeling is different. So I have 1, 3, 2 here, and I have 1, 2, 3 here. Okay. Technically, these two are not the same graph, right? Because, for example, I have the edge 1, 3 here, but the edge 1, 3 does not exist here. So these are considered different graphs. But intuitively, when we look at these two, we realize that they look exactly the same. So if I'm going to prove any property of the first one, that property is very likely going to also hold for the second one, especially if the property doesn't depend on the labels on the vertices. Okay, so this is the idea that we catch with isomorphism. Okay, so what is isomorphism? Isomorphism is basically a relabeling. So I say two graphs are isomorphic if I can just change the labels of the vertices, and then this graph turns into this one. So these two graphs are isomorphic. Now, how do I define that mathematically? I would say that suppose I have two graphs. So again, let's G, B, G, E, G, and H. The two graphs. And isomorphism is just a function that maps vertices of G to vertices of H. Now, I need several properties here. So the first property is that I want it to be a one-to-one correspondence. So I want every vertex of G to be mapped to exactly one vertex of H. So I want F to be one-to-one and onto. Okay. Now, the second property is that, let's say F is mapping 1 to 1 and 3 to 2. So here there was an edge. I want there to be a corresponding edge in the other graph. So I want to say for every two vertices U and V in the vertex set of G, UV is an edge in the first graph if and only if after I apply the function F, FU, FV is an edge in the second graph. Okay, so this is just a very fancy way of saying I'm changing the labels, I'm getting the same graph. Okay. So again, in a lot of cases, we talk about unlabeled graphs, and when we're talking about unlabeled graphs, that's just a class of the isomorphism relation. So the isomorphism relation is an equivalence relation. It defines a bunch of classes. Basically, the point I'm trying to make is that whenever I don't write the labels, that means I don't care about them. Right? Very easy. Okay. Now, we can also talk about other properties. So one property that we very often talk about is the degree of a vertex. So degree of a vertex V it's basically the number of edges that have V as one of its and one of their endpoints. Or another way of looking at this is the number of neighbors of V. Okay, so I show this with D of V, and this is just the number of edges UV. Where basically U is in many, no, too many. Yeah, basically just count how many edges are coming in. So, for example, if I look at Kn, the degree of every vertex is n minus 1, because every vertex is connected to every other vertex in Kn. But for example, here, the degree of this vertex is 3, the degree of this one is 2, the degree of this one is 1. You can also have a vertex of degree 0. If you have a vertex of degree 0, we call it an isolated vertex. Okay. Now, here's our very first theorem. I say that, consider that I have a graph G. If I take the sum of all the degrees, this is going to be twice the number of edges. Okay. We've actually proven this before, but we've proven this without actually talking about graphs. So remember, we had this problem about handshakes. We were saying that if you have a number of people at the party and some of them shake hands, and then for every person, you look at the number of people who have shaken their hand and you sum that up, you're going to get an even number. Now, what was our proof there? Our proof was that every time there is a handshake, it's going to increase the degree of both sides. So here, basically, imagine that my graph has a bunch of people as its vertices, and every time that they shake hands, I'm going to add an edge, right? So this is exactly the same problem. But let's just go over the proof one more time in the language of graph theory. So imagine that I have my graph, and I start by first only adding the vertices without any edges. So I start with the empty graph, and I keep adding the edges one by one. Now, every time that I'm adding an edge, I'm adding, let's say, an edge from vertex U to vertex V. What's happening? This is increasing the number of edges by 1, but it's also increasing the degree of U, and it's increasing the degree of V. So it's increasing the left-hand side by 2. So the sum of the degrees should be twice the number of edges. Okay. Great. Now, we also have this concept of adjacency matrix. And this is a very simple matrix. It's an n by n matrix where I have n vertices. By the way, throughout this course, whenever I say n, I mean the number of vertices. Whenever I say m, I mean the number of edges. Okay, so I'm just defining it once and for all because I will forget to mention this. So my adjacency matrix is just an n by n matrix. Let's call it A for adjacency, where the element at index ij is 1 if there is an edge from I to j, and it's 0 otherwise. Okay. So for example, if I want to consider the triangle, the adjacency matrix of a triangle is just a 3 by 3 matrix, right? But it's just all ones except for the diagonal, because the diagonal entries will correspond to loops, and we don't want to have loops, right? But every vertex is neighbors with every other vertex. Now, this adjacency matrix is actually quite useful. So here's an example. Suppose that I give you a graph. So I give you, for example, this graph, 1, 2, 3, 4. And I say that for every vertex, I want you to find the set of neighbors of this vertex. So I want you to find all the vertices that are, let's say, at a distance of 2. We will define distance soon, but basically I want neighbors of neighbors. Okay. So for example, for vertex 1, neighbors of neighbors, well, that would be 3 and 4. Right. For vertex 2, what is neighbors of neighbors? Oh, yes, 1 itself is there as well, sorry. Yes. For vertex 2, what is the neighbors of neighbors? So the neighbors of 2 are 1, 3, and 4, and the neighbors of those are just 2. And so on. Okay. How can I get the neighbors of neighbors? Well, let's say that I have the adjacency matrix here. I have this matrix A, I just multiply it by itself. I just look at A squared. That would give me neighbors of neighbors. Right. But of course, you have to do some small changes too, because in A squared, I might not have just zeros and ones. I might have other values there as well. But generally speaking, why does this work? So let's say that I have a vertex I, and then there is a vertex J, which is a neighbor of I. So that means that there is a vertex K, where from I can go to K, and from K, I can go to J. Okay. But what is the definition of matrix multiplication? So if I look at the matrix A squared at ij, this is the sum over all k of aik times akj. Right. So for this particular k, aik is 1 and akj is also 1, so it adds 1 to this sum. Right. So if a squared ij is non-zero, that means that with 2 hops, I can go from I to j. So j is a neighbor of I. If aij is 0, it means that I cannot go to j with 2 hops. And generally, you can extend this to more than 2 as well. So if I ask you, what are all the places, all the vertices that I can reach with, let's say, k hops, you just take the matrix A, raise it to the power of k. And also, it not only gives you the places you can get to, it also tells you in how many ways you can get to each of these places. Okay, so adjacency matrices are generally very useful. We're going to use them a lot. Especially, honestly, you're going to use them in 3711 more than 2711. But let's keep going and let's define some more things. By the way, this is the only session where you have to really remember a lot of definitions. But then as soon as we have all of our vocabulary ready, we will just focus on solving problems. And generally speaking, the problems here are not like the counting problems where you have to find an answer. It's more of like proof that this property holds. Okay. So now, look, generally speaking, when I have a graph, in my mind, I'm kind of thinking of these vertices as cities, and I'm thinking of the edges as some roads between these cities, let's say. So a lot of the vocabulary is based on this idea. And these are roads before they were cars, so it's from the time where people would actually walk. So we have the definition of a walk. So what is a walk? If I have a graph, for example, I have this, a walk is basically that I'm going to start at one vertex, I'm going to take an edge. And when I get to the other side of the edge, I'm going to again take another edge and then take another edge and so on. Okay. So I would say that a walk is a sequence of vertices and edges. Let's call it V0, E0, V1, E1, so on, until I have En minus 1 and Vn. Okay, so it starts at a vertex and it ends at a vertex. And the condition is that every EI is an edge that is connecting VI to VI plus 1. Okay. So let's do a very simple example here. Let's say I have this graph. And 1, 2, 3, 4, 5. And let's say that I also now name my edges. So let's say this is edge 1, edge 2, edge 3, edge 4, edge 5, and edge 6. So what would a walk look like? So I can start from 1, and then I can take E1 and go to 2. And then from 2, I can take E3 and go to 3. From 3, maybe I take E3 again and go back to 2, right? And then from 2, maybe again, I take E3 and go back to 3. And then maybe I take E5 and go to 5. This is a walk. Now, importantly, I can repeat vertices and I can also repeat edges. Okay. Now, generally speaking, I don't really need to write the edges in my walk. If I just write the sequence of vertices, it tells me what the walk was. So if I just have like 1, 2, 3, I know that if I want to go from 1 to 2, I have to take the edge E1. Right. So I don't really need to have the set of edges there. And honestly, a lot of the times when I'm writing a walk, I will just write the vertices. Now, why do we define it like this? Because we want the same definition to also work for multigraphs. So remember that later on, when we have multigraphs and we can have several edges between the same pair of vertices, we want to say which one we're taking. But as long as we're working with simple graphs, that doesn't matter. Okay. So I have this definition of a walk. Now, but this is normally not great. So imagine, for example, that every one of these edges is a distance, has some distance. So again, just imagine that vertices are cities, edges are roads between these cities. And let's say that every edge has a distance. And at some point, I'm going to ask, what is the shortest path from 1 to 5? Right? And if I want to find the shortest walk, let's say from 1 to 5, that's not going to be a walk that repeats vertices or edges. Right? So I want to have the vocabulary to talk about good walks, to talk about walks that don't repeat anything, that don't go in cycles. Okay. So here's the thing. We have trails. And a trail is just a walk. Merge the L and K there. A walk that does not have repeated cycles. Sorry, that does not have repeated edges. This is what I call a trail. So if I don't go over any road more than once, then it's a trail. And a path is a walk that does not have repeated vertices. So if I don't go to any city more than once, it's a path. Okay. So a very simple thing. Every path is a trail, but not every trail is a path. Okay. Why is that? Basically, imagine if I'm repeating an edge. If I'm repeating an edge in my walk, I'm repeating its endpoints, at least one of its endpoints, right? But so if I cannot repeat vertices, then I cannot repeat edges. So that means that every path is a trail. But you can easily find trails that are not paths. So here's one example here. I can find this trail. I can go 1 to 2, 2 to 3, 3 to 5, 5 to 4, 4 to 3, 3 to 1. This is a trail because no edge was repeated, but the vertex 3 was repeated there, so it's not a path. Okay. Now, interestingly, my trail started and ended at the same vertex. I call such a trail a closed trail. So a closed trail is just a trail that starts and ends at the same position. And similarly, I can talk about a closed walk. A closed walk is a walk that starts and ends at the same position. I cannot really talk about a closed path, right? Technically, there is a closed path, and that's the path that's just doesn't take any edges, like starts at one vertex, right, and ends there. But otherwise, if my path starts at a vertex, goes somewhere else, if it wants to come back, it's going to repeat this vertex. So that's why it's the definition of path. So instead of that, we define cycles. And cycles are what we wish to have as closed paths. So cycles are basically this. I'm going to start from a vertex V0, and then I'm going to take an edge. It's going to take me to another vertex. I'm going to take another edge, and so on until I get to some vertex. Actually, let me call it K. And then from this vertex, I'm going to take another edge, which takes me to the very first vertex where I start. Okay. So this would be a cycle, and it would be a cycle if it has all the properties before. So if it is a walk and no vertex repeats except for the first vertex that is repeating at the end, and no vertex other than V0 repeats. And also I cannot have V0 somewhere in the middle, right? And V0 appears only at the beginning and the end. Okay. Again, the definitions, when you write them down kind of formally like this, they look complicated, but it's just a cycle. It's that I'm starting from a vertex, taking a bunch of edges, going back to where I came from. But I'm not repeating any other vertices. I'm only repeating my very first vertex. Okay. So, for example, every triangle is a cycle. So here I have the cycle 1, 2, 3. I also have the cycle 3, 4, 5. Okay. So we talked about all of these definitions. Oh, there is one more word. A closed trail is sometimes called a circuit. Honestly, again, I honestly don't care about these words. We only care about path and cycle. Like everything else here is very rarely used. We will use them in this session, but after this session, we will really only talk about paths and cycles. Okay. So here's another theorem that I want to prove. Oh, and by the way, I just realized that here I shouldn't use n because n was supposed to be my total number of vertices, so that's okay. So this is a walk that starts from V0 and ends at Vk. So I'm going to call it a V0 Vk walk, right? So whenever I say a UV walk, I mean a walk that starts at U, ends at V. And also, I can talk about the length of a walk. So the length of a walk is just the number of edges. Okay. So for example, if I consider this cycle like 1, E1, 2, E3, 3, E2, 1, this has length 3. And of course, I use the same notion of length for trails, paths, and cycles. So whenever I'm talking about length, it's the number of edges. here's my first theorem. I say every UV walk contains a UV path. Okay. Or actually, I can say it in a different way. It's not exactly equivalent, but it's the same idea. If there is a walk from U to V, then there is a path from U to V. Now, the opposite of this is trivial. If there's a path from U to V, then there's a walk from U to V because every path is a walk, right? But why is the case? Why is this the case? Why is it that whenever I have a walk from U to V, I will also have a path? Remember that in a walk, I can repeat edges, I can repeat vertices. I really have no restrictions. The only restriction is that I have to respect the graph. When I'm at a particular vertex, I can only take the edges that have one of their endpoints there, right? But in a path, I have to additionally make sure that I'm going over every edge and every vertex at most once. Okay. Give me a proof. If there is a walk from U to V, then there's a path from U to V. Okay. Here's my first proof. And in this proof, I'm just going to use that order. So I'm going to say, consider the shortest walk from U to V. Okay. So let's call it P because it's going to be a path. Be the shortest walk from U to V. Now, there is a problem with this statement already, because I'm not sure that there is just one shortest walk. So I cannot talk about the shortest walk, right? Because maybe, let's say the shortest walk that I can have from U to V takes 3 edges. And let's say that there are many different ways of going from U to V with 3 edges. So instead of that, I'm going to say let P be a, oh, I removed the wrong word. Yeah. So let P be a shortest walk from U to V. So maybe there are other walks of the same length, but I'm saying basically, how am I using well ordering here? I'm saying look at the set of all natural numbers that are lengths of walks from U to V. This set is non-empty because there is a walk from U to V. And every non-empty subset of natural numbers has the smallest element. So I can talk about a shortest walk from U to V. Okay. So let P be a shortest walk from U to V. Now, I'm going to claim that this P is actually a path. I claim P is a path. Okay. Let's prove this by contradiction. Suppose it's not a path. Okay. What happens if P is not a path? Okay. It means that some vertex was repeated in P. So basically, it means that I started from U, and then I went somewhere. I got to some other vertex, let's call it W. Then I did something else. I came back to W, and I kept going until I got to V. That's what it means for this not to be a path. It's a walk that is not a path. So there should be a vertex W that is repeated. Okay, but here's the thing. Another way of visualizing this, and maybe it's better to visualize it like this, is that I start here, I go somewhere, come back to W, and I keep going until I get to V. Okay, I don't need this cycle here. Who cares about this cycle, right? I can just take this path. I can go from U to W, and instead of going around this cycle, just go directly to V. That's a shorter path. It has fewer edges because I'm not going through the edges of that cycle. This contradicts with the original path being the shortest path or a shortest walk from U to V, right? Because this one is a shorter walk than this original. So the shortest walk has to be a path, which means that whenever I have a walk from U to V, I also have a path from U to V. Now, the first thing that I wrote here is a little bit stronger. I'm saying every UV walk contains a UV path, right? So this is not the same as this one. Basically here I'm saying that if there is a walk from U to V, then you can find the path from U to V, but I'm not saying anything about the relation between the walk and the path. But here I'm saying if I give you a walk from U to V, you can just take some subset of it and it's a path from U to V. But the proof is very similar. So the proof for the first part is that suppose I have a walk from U to V. So it starts from U, it goes to some vertex, it goes to some other vertex. Maybe at some point it has a cycle, it comes back here, right? And then it keeps going. And then maybe it has another cycle. And then it keeps going, and so on. But I can use an idea like before, right? I can find the first cycle and I can just remove it. And now I have the rest of my walk. Again, I go through this walk, find the first cycle, just remove it. So keep removing the cycles from this walk. You will eventually get a path, right? So if I give you a walk, you can always find a path that is actually a subset of this walk. Okay. Now, let me give you this problem. This is the famous problem that actually started this whole field. This is the Königsberg bridges problem. So the problem is this. We have this graph. Let me actually draw it exactly like here. And it's actually a multi-graph. So I have two edges connecting these two. I have one edge here, one edge here, two edges connecting these two. I have one edge here. Okay. So again, at the time of dinosaurs, Euler was at the city of Königsberg, and this city had a bunch of islands that were connected to each other by a bunch of bridges. So our vertices here are the islands, and the edges are the bridges. And the reason we have multiple edges is that between some pairs of islands, people built more than one bridge. Okay, so let's call this 1, 2, 3, 4. So they built two bridges between islands 1 and 2. Now, one problem that people in this city really loved was that they wanted to start at any of the islands and find a closed walk. So starting from here, finding a closed walk that goes back to the same place. But they wanted this walk to be a trail, so they didn't want to cross any bridge more than once. And they also wanted to cross all the bridges at least once. So basically the idea is I want to start at vertex number 1. I want to see every one of the bridges at least once, and I want to come back, sorry, every one of the bridges exactly once, and I want to come back to vertex number. Okay. So Euler proved this is not possible, and that's where graph theory started, because this was the first time someone said geometry doesn't matter. Okay. Why is this not possible? So just look at vertex number 1. Let's say, first of all, if I can do it from one of the vertices, I can do it from any of the vertices, right? So that one is easy because at the end of the day, it's a closed walk. So let's say I want to start from vertex 1. I start from vertex 1, and I have to take one of the edges out, right? So I will take one of these 3 edges to go out of vertex 1. At some point, I have to come back to vertex 1. when I come back to vertex 1, it's going to use a second edge. And then I'm going to take the third edge to go out of vertex 1. But now I have no edges remaining to come back to vertex 1. So basically, because the degree of vertex 1 is odd, it's impossible to have the same number of entries and exits to vertex 1. So it's impossible to go all around. Okay. So very simple problem. People were not great at math in the old days. They're still not great. Okay. Like, honestly, I don't just understand this whole story. Like, they say that for hundreds of years, people in this town were waking up every day, going and trying this. No one saw that there are 3 bridges here. Okay. Great. But now we want to talk about some other things. We will come back to this. But I want to talk about connectivity. So we say that vertex U is connected to vertex V. U is connected to V if there exists a UV path. Okay. So if I have a path from U to V, I say U is connected. Be careful about the terminology here. When I say 2 vertices are connected, it doesn't mean that they're directly connected or neighbors. So if there is an edge between 2 vertices, I say that they're neighbors or adjacent. When I say they're connected, it means that there's a path between them. Okay. And of course, based on the previous theorem, we've seen that this is the same as saying there is a UV walk. It doesn't really matter. Okay. But now based on this, I can say when a graph is connected. I say my graph is connected if every vertex is connected to every other vertex. So a graph G is connected if every pair of vertices are connected. Okay. So basically, this is this idea that I can go from everywhere to everywhere. So for example, we hope that the graph of the internet is connected, because if it's connected, it means that I can send messages from every computer on the internet to every other computer on the internet. There is a path. There is a sequence of connections that connects them. I think in practice, it's not really connected because North Korea, but yeah, a graph is connected if every pair of vertices. But now what happens if graphs are not connected? We can talk about connected components, right? So imagine that I have a graph like this. Okay. I would say that this graph has 4 connected components because it has 4 parts and each part is connected, right? So a connected component, and this is one of the things that we will work on a lot in this course. A connected component, or sometimes we just call it a component or CC, is a maximal connected subset of vertices. So it's a set of vertices that are all connected to each other, but I cannot add any other vertex to keep the same connectivity constraint, right? So for example, these 3 vertices will not be a connected component because they're not maximal. I can add another vertex and still have all of them connected. But all 4 of them, like this, is a connected component. Okay. So for every graph, I can talk about its number of connected components. And if it has exactly 1 connected component, then it's connected. Okay. Now, what I'm interested in is what happens when I remove some vertices or some edges. So if I have a graph that is connected and I have an edge, but removing that edge would make the graph disconnected, then I say that that edge is a cut. The same thing for a vertex. If I have a connected graph and I have one vertex and removing this vertex, and of course, when I remove a vertex, I have to remove all the edges that are adjacent to it. If removing this vertex increases the number of connected components, I say it's a cut vertex. And yeah, for cut edges, I can also extend this to all graphs. So even if my graph is not connected, I can say this is a cut edge because removing this edge will increase the number of connected components, right? But generally, when we talk about cuts, we're usually talking about cuts in connected. Okay, so let's prove some more theorems. Here's a theorem. Let's say I have a graph with n vertices and m edges. So a graph with n vertices and m edges. I want to say that it has at least n minus m components. First of all, this only makes sense if the number of edges is less than the number of vertices, because otherwise I'm saying that, I don't know, it has at least -2 components. Well, of course, right? But basically, if I have a graph with 100 vertices and 20 edges, I have at least 80 components. Why is that the case? So this is an idea that we will see over and over again in a lot of the problems. We can start the graph as an empty graph, and we can keep adding the edges in our graph one by one and see what happens. So originally, let's say I have the empty graph, and this is the empty graph on n vertices. So I have vertices 1, 2, 3, 4, 5, so on to n. Okay. So originally I have n connected components because every vertex is its own component, right? Now I'm going to keep adding my edges one by one, and I don't care in what order. So just give some order to the edges, call them E1 to EM. I'm going to add them one by one. When I add the first edge, when I add E1, what's going to happen to my connected components? It's going to merge two of my connected components into one, right? So previously, 2 and 5 in this case were two different connected components, but now that I added this edge, they're the same connected components. So the number of connected components went down by 1. Now, let's say I keep adding my edges one by one. In some cases, when I add an edge, the number of connected components goes down. So for example, let's say I add this one, the number of connected components is decreased by 1. Let's say I add this one, the number of connected components is decreased by 1. But it's also possible that I add an edge and my number of connected components does not change. So for example, if I add the edge from 1 to 4, that doesn't change the number of connected components. Now, when does this happen? It happens when the two endpoints were already in the same component, right? So in this case, adding the edge 1, 4 doesn't really change anything about my components because there was already a path from 1 to 4, right? But if I add an edge from 3 to 5, since there was no path from 3 to 5 before, they were in different components, their components get merged. Okay. So now I have the proof for my theorem. I'm starting with the empty graph, which has n components. I'm adding the edges one by one. Every edge is in one of two cases. Either it reduces the number of components by 1 because it's connecting two vertices that were in different components, or it doesn't change the number of components because the two vertices were already in the same component. Okay, so since I'm adding m edges and each one can decrease the number of components by at most 1, I'm going to have at least n minus m components at the end. Okay. Again, very importantly, I'm not saying that I will have exactly n minus m components. I'm saying I will have at least n minus m components. Okay. This gives us a very simple corollary, which is actually quite important. So let's say I have a graph on n vertices and this graph is connected. What is the minimum number of edges that I should have in order to get a connected graph? N minus 1, right? Because a connected graph has one connected component. So basically this M should be N minus 1. So the corollary is that every connected graph has M greater than or equal to N minus 1. And again, M was the number of edges, N was the number of vertices. So for example, if I have 4 vertices, I need at least 3 edges to connect them all together. So if I have 4 vertices, I can, for example, have this graph, or I can have this graph, right? These are connected and they have N minus 1 edges, which is exactly 3. So we really like these graphs. We really like the connected graphs that have the minimum possible number of edges. And actually, you will see that half of this course is about them. And we call these trees. So a tree is a connected graph with N minus 1 edges. Okay. Now I'm going to prove our first theorem about trees. This is the theorem. I say, let G, let's say VE, be a graph. And as usual, I show the number of vertices by N and the number of edges by M. Then these 3 conditions are equivalent. Basically, I'm going to give you 3 different ways of defining trees. Condition 1 says that G is connected and has N minus 1 edges, which is basically the definition that I used here. So G is connected and M is N minus 1. Condition 2 says that G is connected and has no cycles. Interesting point. If you look here, I don't have any cycles. So generally, I'm going to claim that trees don't have cycles. So G is connected and has no cycles. Okay. And condition 3, can you guess? G has N minus 1 edges and no cycles. Okay. M is N minus 1 and G has no cycles. So basically what I'm saying is that consider these 3 properties: being connected, having N minus 1 edges, and having no cycles. If you have 2 of them, you will definitely have the third one. And any 2 of these properties is enough for a graph to be a tree. That's what I'm saying. So being connected and having N minus 1 edges is equivalent to being connected and having no cycles, which is equivalent to having N minus 1 edges and having no cycles. Okay. How would you prove this? So again, as before, we have to somehow show that each one of these conditions implies each of the other ones. I'll do some of them. So let's say 1 implies 2. So assuming 1, I want to prove 2. I'm assuming that my graph is connected and I have N minus 1 edges. I want to prove that I have no cycle. I'm going to use the same technique as before. I'm going to say I start with the empty graph. I keep adding my edges one by one, and I just look at what happens. Okay. So start with the empty graph. and add edges one by one. Okay, I have to add m edges. Now, what do I know? I know that I have n minus 1 edges because I'm assuming 1 trying to prove 2. Okay, so I have to add n minus 1 edges. But also, I know that after I add these n minus 1 edges, I should get a connected graph. So every time that I was adding one of these edges, I said that the number of connected components either remains the same or decreases by 1. But the fact that I have a connected graph at the end means that every one of these edges reduced the number of connected components, right? So every edge, let's call it EI, reduces the number of connected components. Because otherwise, I cannot have just one connected component. Okay. Now, what do I want to prove? I want to prove that G is connected, but I already have that in my assumption. The thing that is actually important is that I want to prove G has no cycles. Okay. So how does a cycle form? As I'm adding these edges one by one, when do I get a cycle? So here's the thing. Just imagine that I have my vertices and I'm just adding the edges one by one, right? Let's say I keep adding the edges until the first cycle forms. As soon as I see the first cycle, I stop, okay? So in this case, let's say I add this edge and it's a cycle, so I stop. Okay. Because this edge was the last edge that created a cycle, what does it mean? If the two endpoints are U and V, actually, let me use a different edge. Let me use this edge. So if the endpoints are U and V, and this is the first time that I'm getting a cycle, it means that there is a cycle that includes U and V, right? But that means that U and V were already in the same connected component. They were already reachable from each other. Because what is a cycle containing U and V? It's just this edge plus a path from V to U, right? So there was already a path from V to U, so U and V were in the same connected component. Now, based on this, I can again divide my edges into two categories: edges that create cycles and edges that don't create cycles. As I'm adding my edges, if the two endpoints of this edge are in the are in different connected components, let's say first, let's do that case. Let's say I'm adding this edge. I've already added two of my edges. I'm adding my third edge. And let's say the two endpoints are in different connected components. This is not going to create a cycle because there was no path between the two endpoints before, right? But now, let's say that the two endpoints were already in the same connected component. So let's say I take this vertex and this vertex, they were already in the same connected component. So there was already a path between them. So now if I add an edge, that will create a cycle because this edge plus the path that existed before is a cycle. So the edges that create cycles are exactly the edges that are added between vertices of the same connected components. But we don't have any of those, right? Why don't we have any of those? Because my assumption is that G is connected and I have n minus 1 edges. So every time that I was adding an edge, I was reducing the number of connected components. So every edge was connecting two different connected components. So no edge can create a cycle, so I don't have a cycle. Okay. So this is the proof from 1 to 2. If G is connected and we have n minus 1 edges, we have no cycles. Okay. Now, let's go from 2 to 1. Let's do the opposite of this. Because actually it's quite easy to do the opposite direction of the same argument. So 2 to 1 means that I'm assuming G is connected and I have no cycles, I want to prove that I have n-1 edges. Okay. First of all, if I go from 2 to 1, in my assumptions, I have that G is connected. I want to also prove that, so I don't really have to do anything for the connectedness. It's really about this part, right? So I'm assuming 2, I want to prove 1. I just have to say that the number of edges is exactly n-1. Okay. But my graph is connected, so I have at least n-1 edges. I have proven that before, right? This one. Every connected graph has at least n-1 edges. Okay, so in order to prove I have exactly n-1 edges, I have to now prove I have at most n-1 edges. So I have to prove it's impossible to have more than n-1. Okay. Again, I do the same thing. I start with the empty graph, keep adding my edges one by one. Remember, I have no cycles. So every edge has to connect 2 different connected components to each other. It cannot be between vertices in the same connected component. So every edge decreases the number of connected components. But I can decrease the number of connected components at most n-1 times, because after that I will just have one connected component and I can no longer find the edges that connect vertices in 2 different connected components. So I have at most n-1 edges. And based on this one, again, I have at least n-1 edges, so I have exactly n-1 edges. Okay. Now, at this point, we have basically proven that 1 and 2 are equivalent. We have to just prove that somehow they're equivalent to the third one. Okay. So let's prove this one. Let's prove that 2 implies 3. So if G is connected and has no cycles, that means that the number of edges is n-1, and we have no cycles. This is the same proof as this one that we just did. Actually, it's very similar. It's just saying, look, I have this graph G, it's connected, it has no cycles. So the no cycles part is the same, right? I have it in my assumptions, I want to prove it, I'm happy. I just want to prove that it has n-1 edges. But again, just add the edges one by one. In order to make it connected, it has to have at least n-1 edges, right? And also, since I have no cycles, I cannot have more than n-1 edges by the same argument as before, because every edge is reducing the number of connected components by 1. So I have exactly n-1 edges. So 2 to 3 is easy. Okay. I can do this basically in any combination. Let's just do that 3 implies 1, and then that would be enough to prove that all of them are equivalent. So I have n-1 edges and no cycles. I want to prove that I have n-1 edges and I'm connected. So again, the part with n-1 edges doesn't need a proof. I just need to say that if I have n-1 edges and no cycles, I'm connected. Okay. Again, the same argument. Just start with the empty graph, keep adding the edges one by one. I have no cycles. So every edge is connecting 2 vertices that were in different connected components. So every edge is reducing the number of connected components by 1. I'm starting with n connected components. I'm reducing the number of connected components n-1 times. So I have to end up with 1 connected component, which is exactly the definition of being connected. Okay. So you see, all of these things are basically saying the same thing. Okay. But now, based on very similar ideas, I can prove another nice theorem about cuts. So I say an edge, let's call it E, is a cut if and only if E is not part of any cycle. Okay. Very importantly, in this course, whenever we say if and only if, and not just in this course, in general, in mathematics, whenever we say if and only if, you have to prove that the first one implies the second one and the second one implies the first one. If you forget one of the two sides, that's considered a logical error. You get an F in this course. Okay, so one of the things that are never allowed in this course are logical errors. Okay, and irrespective of how you're doing in the rest of the exam, if you make logical errors, it's an F. But you will not make logical errors because I just threatened you with this. So, and similarly, when I say prove something is minimum, so I say, for example, here, what was it? We were saying that if a graph is connected, it has at least n-1 edges, right? But if I said it in a different way, if I said that prove that the minimum number of edges needed for a connected graph is n-1, you will also have to prove two things. You will have to prove that you cannot have a connected graph with less than n-1 edges, and you will have to prove that you can have a connected graph with n-1 edges. If you forget one of these two, it's again a logical error. Okay. An edge is a cut if and only if the edge is not part of any cycle. Why is this the case? Remember, and I'm talking about connected graphs here. Actually, I don't need to assume connectedness, but let's say my graph is connected. So an edge is a cut by definition if removing it would make the graph disconnected. So I'm saying that the removal of the edge E makes the graph disconnected if and only if E is not part of any cycle. Okay. So let's do this side, which means that I'm assuming E is a cut. Okay. So assume E is a cut. Okay. So let's look at my edge E. It's going to connect two vertices. I'm going to call them U and V. Okay. I know that initially my graph is connected, but if I remove E, the graph will be disconnected. So if I remove E, the graph will actually disconnect in two parts, the part that is connected to U and the part that is connected to V. Right? But then E is the only edge that is connecting these two parts together. That's my intuition. But what I want to prove is a much simpler thing. I want to say that E is not part of any cycle. So I say, let's do proof by contradiction. Suppose E is in a cycle, let's call it C. Okay. What does that mean? That means that I basically have a cycle that contains E, but also contains some other parts. Let's call this C. Okay. You can already see from this picture that removing E cannot possibly change my connected components. But we have to prove that a little bit more formally. So what does it mean that my graph was connected before? It means that for every two vertices A and B, there is an AB path. Okay. Now I want to say that it remains connected after removing E. Okay. So let's say I have a vertex A and a vertex B. I mean, they don't necessarily have to be on two sides. I don't care. And there is a path from A to B. Okay. I consider two cases. My first case is if the path from A to B does not go through E. Right? So I have a path from A to B and it doesn't even cross the edge E. If I remove the edge E, that path is going to still be there. So they're still going to be connected. So this is the easy case. The harder case is that I have a path from A to B, but it does go through the edge E. Okay. But now I can do this. I can say, take the rest of the cycle in place of E. So start from A and go to U. But then because E is removed, you cannot take E. So take this other side of the cycle until you get to V. And then from V, take whatever your path was before to B. Okay. Now, this is not necessarily a path. Maybe this is a walk. But we've already proven that if there is a walk from A to B, there is a path from A to B. So maybe the orange part is not a path, but the orange part definitely includes a path from A to B. So what did I prove? I proved that for every A and B, there was a path from A to B before, so there is still a path from A to B after removing E. But that contradicts with the assumption that E was a cut. Because by definition, I said E is a cut if it increases the number of connected components, but my graph was connected before and it's connected after. So this contradiction shows that E cannot be part of a cycle. So we proved one part of it. Now we have to prove the other part. So what is the other part? It's that assume E is not in any cycle. Prove that E is a cut. Okay. Again, proof by contradiction. Suppose that E is not a cut. What does it mean? I had E, I had my vertices U and V on the two endpoints of E, and U and V were reachable from each other before. There was a path between U and V, just a path consisting of the edge. Now I'm removing E, and E is a cut, right? So, sorry, no. E is not in any cycle. I'm removing E, and E is not in any cycle. I want to prove that there is no longer a path from U to V. Let's do it again by contradiction. Suppose after removing E, there is somehow a path from U to V. Let's call that P. But then adding P to E creates a cycle that contains E, which contradicts my assumption that E was not in any cycle. Okay, so that's it. So we proved that an edge is a cut if and only if it is not part of any cycle.